The SD Ruby podcast is brought to you by New Relic.
So I'm going to talk about a problem in Ruby, the Ruby implementation, and what I did to partially solve it. Ruby 2 will be better. It's still not very good. And so this is about how to, so the problem was Ruby startup time. You've all done this, Rails console, and you sit there and you're waiting, and you keep waiting and waiting. This is with our Rails app at TDM, at Solana Labs, and it sits there for a while, and maybe you start to see some logging spew while it's gradually starting, and then eventually you get your prompt. And so before I started this work, it was 17 seconds for me trying to get a prompt in the Rails app. And it's pretty painful if you're trying to get work done. So, so I set out to fix that. And it's better now. I'll give you the bottom line. After the patches, which are going into Ruby 2.0, have gone in, you sit there, you still have to sit there for a bit, and it's still kind of varying how long it takes, but it's more like 9 seconds. So it's half as long. And that's about how much across the board it got sped up. And so I'm going to talk about what the problem was, but perhaps more to the point, what the process was of diagnosing it and fixing it, and show you tools which are general to fixing any kind of problem if you want to study a problem in the Ruby interpreter itself or in a C extension module if you happen to maintain one of those. So I like 4 major steps for trying to fix some kind of performance problem. First, you measure the problem. You can't fix, you can't measure. You don't even know if you're fixing it. Then you profile to find where the problem is. Then you can fix the problem. And then you repeat until you're either it's fast enough or you're tired. So step 1. So I already showed you how long it takes. Let's measure a bit more. If you look at how many files our Rails app was loading, there's an array in the definition of Ruby that contains all the files that have been loaded. All the Ruby source files have been loaded, and that array is over 2,000 long in our app. And I don't think we're atypical, particularly in that. You have a bunch of libraries, Rails, a bunch of other libraries, some files of your own. It adds up. And so we know that the problem is startup time. What's it doing in startup? Well, it's requiring a bunch of files. So surely just purely requiring files and nothing else can't take that long, right? Well, so let's just require thousands of files. So I went and made 10,000 empty files, and I had a little loop that did nothing but load the 10,000 empty files, acquire them. And that actually was pretty slow. So I did more than 10,000. So it's slow enough that you have a not totally unreasonable number of thousands of files. It could take seconds. And perhaps more troubling, if you do the division, you see that it's taking, even though there are only a small number of files, it's taking for each file you require 1/10 of a millisecond. Now, 1/10 of a millisecond, that's an eternity in CPU time. That's 100,000 nanoseconds. That's time enough, if you've seen the numbers that every computer programmer should know, which originate, if I have it right, with Peter Norvig and popularized by Jeff Dean as well. That's time enough to fetch 1,000 separate items from main memory. We don't have that much work to do just to require an empty file. And then the worst part is it actually takes longer as we keep going. after we've required 8,000 files, it takes more like 0.3 of a millisecond to require one. In fact, every time we double the number of files we have, we not only double the number of time we're spending, we quadruple it. We double the amount of time we're spending per file. So that shouldn't be. The amount of real work to do to require an empty file does not increase. So this is already offensive if you're trying to fix performance problems. And perhaps more practically, it's something that's slow already, that's slow similar to the thing we actually want to fix, and it's simple. So we'll drill down and we'll fix this. So profile this. So the best profile I've found for this kind of work is the Linux tool called perf. I'm sure many of you develop on Macs or something, but you probably all deploy on Linux, so you can all do this. And perf, it probably comes with your Linux distribution if you have anything recent at all. So the way you use it is actually pretty simple for starters. You just say perf record, and then the command that's slow. And that will spit out a bunch of data to a file, and then perf report will go and read that file. And there's a flag, you can change what the default name of the file is, but it doesn't matter. And so here's what perf report says. It says, well, it actually gives you a nice browser in the terminal, but I'm rendering it for the slide, rendering it statically. And it gives you a breakdown of where it's spending the time. And now, the way it works is actually very, very precise. It uses features in the processor to count down precise numbers of clock cycles. And when the counter gets to 0, it fires, and it gets to look, okay, where's the instruction pointer? Where exactly in the machine code are we right now? And it remembers that. And then it resets the special register in the CPU that will count again an exact number of cycles. And moreover, perf is in cahoots with the kernel, so when your process gets descheduled, when it sleeps or something, that register just gets saved. It's restored to that value when it's back. So it counts the exact number of cycles that actually were spent in this process, and gets precise samples. So here's what the tally is. And the thing at the top is in the C library, and the number 5 thing is in the kernel. That's what you get because perf is a system profiler. It's just as comfortable profiling no matter what it is, even the kernel. But we're just inside the Ruby interpreter, so you can filter it. And now here are the top 5 items within. This is the share of time being spent doing our simple require empty files task in different functions in the Ruby interpreter. And this is actually pretty stark results. This says that just 3 functions, if you add that up, is 80% of the time you're spending in the interpreter. And moreover, if you look at those, 2 of those, RB feature P and loaded feature path, those are both part of the implementation of require, which is good because that's the thing we were stressing. And the one at the top actually is a very generic helper function. It's used all over the interpreter. It basically is a C function that calls 2s on an object and gives you back the string result. And usually you hope it's already a string, but it gives you the string result. And so that's actually not very informative because it's called from everywhere. We really want to know not the fact that we're spending a lot of time there, but what's calling that so many times. And so that calls for a little more advanced technique, a little better profiling. That calls for call graph profiling. So we want to know not only what bit of code are we catching the CPU actually in when we sample and sample and sample, but what's the caller of that code, what's the caller of that code, etc. And perf supports that. It's great. You just add -g when you record. Unfortunately, it's not quite so simple with the Ruby interpreter. It makes it tricky. The recipe is kind of complicated at the end. So to save you taking notes, it's already on the web. It's in a blog post that I put up a little while ago. Here's a summary. You have to clone the Ruby interpreter, apply my patch, which is there so that step 3 doesn't make the interpreter not work, and then add a flag to the build, and then you get to do perf record -g, which is easy in perf report. And here's that patch. You don't really want to know what this is. I can answer later if somebody wants to know. So this is the recipe. This will get you a version of MRI that's just tweaked so that it's possible to see what the colors are of the code that's running, so the perfect core sheet can work. And here's what you get when you run this. On our simple little task, just requiring thousands of empty files, you see you now get to expand out what the various colors are of each bit of code. And you see that for RB string value pointer, the main color is RB feature p again. And in fact, the other color is RB require safe, which is also part of the requirement notation. So basically all our time is in the requirement notation, and here's exactly where it is. The exact function is where it is. And in fact, RB feature p is totaling, again, about 80%, 77%. So that's our culprit, that function. Here's what the function looks like. So this is, now we're on to step 3, fix it. So to fix, we better understand what this is. So it's some long C function. Here's a summary of it. So the job of this function is, we're calling require. So we said require foo. You can say require foo and then say require foo again. And we don't want to go and actually read foo.rb twice and parse it twice and run it twice. So, of course, the implementation has to check, oh, we already required that. Don't do anything. And this is the function it calls to do that check. And you can see here how it works. It goes through an array, the array called loaded features, or dollar double quote, which is, we saw it earlier when we were counting how many files were loaded. It's the array of all the files that have been loaded by this interpreter, or that have been required, rather. And we iterate through that array. We iterate through that array. We call string value pointers. That's why that shows up in the profile. And we call loaded feature path, which is why that shows up in the profile. And loaded feature path is a function that goes and decides whether the foo we're looking for matches the user live blah 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 foo.rb that's in the array. So we're iterating through this array. And it gets to thousands of elements. And every time we add one more element, we have to iterate through the whole array to see that it's not already there. So that's why it's slow. That's why it's quadrupling when you double number of files. That's why it's taking quadratic time. So this is what we have to fix. So those of you who are algorithms connoisseurs know what the outline of the fix is. You need a hash table. Unfortunately, it's a little more complicated than that. I'm not the first person to have spotted this problem and to have said, well, gosh, we need a hash table, not this iterating through an array. Unfortunately, due to complexities in the semantics that have accreted over the years, and a desire to preserve those semantics exactly to be 100% bug compatible with previous versions of Ruby. Some of which is probably justifiable, some of which I think is not, but it's the way that the core developers wanted to do it. It's not simple to just stick a hash table in there to do this job. And one reason is that loaded features path function, which is not just a simple string comparison. It's deciding whether this short name, require foo/var, matches a full path name with an extension. And the other reason is that, well, loaded features, it's an array. It's exposed to Ruby as an array. And there's no notion in the Ruby language of an array that might change but can't be changed by the user. And nobody bothered to introduce that notion just for this. So the user can modify this too. And if we want 100% bug compatibility, we need to preserve the exact behavior that that older versions of Ruby would have happened to have if the user goes and mucks with this array. They could go and remove an entry, and then we would not realize we'd loaded that file before. We'd go and load it again happily if someone required it, etc. And So we have to preserve that. That's the way the core developers want to do it. And so now you have this hash table. At the same time, the array can be mutated, and you have to keep the hash table in sync somehow. And that wasn't trivial either. And that was both of these got in the way of people who tried to fix it before. But it is possible. And I submitted a fix, and I'm happy to answer questions about it. And there it is, and it went into Ruby 2.0. And so step 4, repeat, which means measure again. So go and repeat the same required thousands of empty files test. And hey, it's actually a lot faster. It's over 4 times as fast for large numbers of files. It's still, you can see the number of time per file is creeping up. It's still quadratic, in fact. But at least we improved the constant file a lot. So we're not done repeating. I'll pause here for questions, and I'll continue to the next phase. I see questions?
Over here? Question?
Yeah, but there's a mic.
Oh, sorry.
So he'll go over.
Oh, I was just wondering, I know that you're talking about like Ruby and not necessarily like Rails and applications and stuff.
Yeah.
But is there something about the requires that us as developers can take out some of the legwork? Like, for instance, the fact that we don't require extensions, or that you can use relative paths.
Yeah,
is there parts of it that it has to check if it's not absolute?
There's not really much you can do to mitigate this, other than upgrade Ruby 2.0 when it comes out. Upgrade to a patch version of Ruby with these patches. There's instructions, if you go to the bug report that I linked to, there's instructions for how to apply the patches. Or just have fewer files, unfortunately.
Sorry. I was just wondering, so why did you use the best, or why is it using the best of 5 for the time estimation?
That's a common practice in getting an accurate measure of how long something takes on a computer, especially if the computer might be doing other things. The thinking is there's a lot of effects that can skew how long something takes when you time it, but generally it will skew it by making it take longer. Right, like something might be loaded in some way, or the cache might be cold, and you end up measuring it with a warm cache. And so the most stable measurement you can make is what's the best out of a reasonable number of tries. That's why I did that.
Is there another question on this one here? Where does autoload fit into this? I mean, was the autoload like created to kind of as a band-aid to this?
I don't know the history, but that seems likely, yeah. Yeah, I don't know.
Now that autoload is deprecated, are we gonna go, I mean, are we gonna head back where we are today because there are so many gems out there that are using autoload and
yeah, well, so one bit of history that I do know is this was not nearly so bad in Ruby 1.8. It actually got a lot worse in 1.9, partly because of the change to storing absolute paths in loaded features rather than relative paths. And consequently, this loaded feature path thing, the matches got a lot slower, and there's the next step we'll see actually also became much slower, basically arose with that change. And so this startup time problem got a lot worse with 1.9. The problem was raised, and people tried to fix it in these ways in time for 1.9.3, and they didn't succeed in really fixing it, but somebody did go in and add a little more spaghetti code just to optimize common cases. And so 1.9.3 is like 30% faster, I think, than 1.9.2 to start out. So that's as much as you really know. But it's still, 1.9.3 is still slower than 1.8. It's one of the pain points people have when they belatedly upgrade from 1.8.
Yes.
I was just wondering if you're involved at all with JRuby, and if you know if this problem is going to be fixed in JRuby as well by using a hash table.
I am not involved in JRuby. I should know. I don't actually know whether they suffer from this problem.
It's not cool.
Sorry?
I guess I'll have to look.
Yeah.
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 Cool.
Good question. All right. Okay, one more and then I'll move on to this part two. No problem.
So you can apply your patch to older versions of Ruby.
Right.
So I can apply it to 1.9.
Yes.
Okay.
Yeah. In fact, we do that
Okay.
for our development. Yeah. And the instructions are in that bug report that I linked, and I'll link it at the end too.
Cool.
Okay, so it's still slower than it really should be. And if we go to our thing we really care about, we sped this up too, it turns out. Not by quite as spectacularly as the isolated micro benchmark, but this is substantially faster, but still embarrassingly slow. So, okay. We profile again. Skip straight to the call graph profiling this time. And this time, you look at all these entries, and every one of those is in the GC. The only function name mentioned, though, is not the GC, is st4e, which is a generic helper function for walking hash tables. But its principal callers are the GC. So we're either marking some kind of item, or marking some other kind of item, or marking another kind of item, basically, or all the things that are going on. So somehow we're spending a lot of time in the garbage collector. And unfortunately, we can't really read off from this what the problem is, why we're spending so much time in the garbage collector. We really want to know what is causing the calls into the garbage collector that are so slow. Alternatively, we could try to go and make the garbage collector faster, but that seems like a bigger project. So leave that for another day. We want to know what's calling the garbage collector with these really long calls. And so fortunately, there is an option to perf that can do this. It's not an option up in perf because I made it up in order to solve this problem. But there's a patch, and the perf maintainer is maybe looking at it, and maybe you'll see it in a future version of Linux. I sent it upstream, and you kind of acknowledge it. So, but you can always download the patch and rebuild the perf, and it's not too hard. And so if you pass that option, what it says is take, the problem here is that the way that the Ruby garbage collector is implemented is this giant mess of helper functions that mutually recurse. So you get into garbage collect, and then it calls the function to mark one kind of thing, and that refers to other objects, so it calls the functions to mark those kinds of things, which calls the functions to mark other kinds of things, etc. And they're all recursing on each other. And the different call stacks all look different at the close-in end, because it's all the different paths you might have followed within the heap. But you just want to ignore all that internal to garbage collect, and treat garbage collect as a black box, which is what I call the option this. And so that's what the option does. It cuts off all the call stack inside garbage collect, and just shows you what are the callers of that, plus any time it's not in garbage collect. And so here's our answer. We're spending the great bulk of the time that's in garbage collect, we're spending in allocating a new string in order to call Ruby file expand path, which is in order to expand a relative path into an absolute path, in order to expand the load path in the required implementation. And this is in the profile of the actual thing we care about, which is starting the app. We're spending the great bulk of our time just expanding the load path. And so that's ridiculous in itself. And so the solution is we should cache the result of that work. So in Ruby, before these patches, every time you call require again, it says, oh, well, here's the reason it has to do this. Oh, well, I've got to go through the list of all the loaded features, right? And I've got to decide if your foo/bar you're requiring matches userlib blah, 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 foo bar.rb, or matches whatever it is. And in order to do that, for whatever reason, the implementers decided that They need to actually detect whether the user lib blah 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 that comes before the foo/bar.rb is actually in the load path. If it's not in the load path, they're going to assign that it's not a match. And so this means that when they find something that looks like it might be a match, they have to iterate through the load path. But the load path is just this array of paths that the user specifies, and it may well contain relative paths. It may contain paths that begin with tilde. It may contain, perhaps you're on Windows and it contains paths that don't have a drive letter. There's any number of things it can contain that it's allowed to contain, and but loaded features is stored all as absolute paths, and so it has to expand those into absolute paths. And there's actually no good reason why it should even be slow to do that. It's because the garbage collector is not very smart about when it decides to run. But it is. And rather than fix the garbage collector, at least we can fix the invocation of the garbage collector better. And so we face similar complications to last time. In this case, there are very good reasons why you might mutate load path. Ruby gems has to mutate load path so you have gems that work. So we really do need to support that. The other things to mutate, but again, it is possible to fix. And so I did. It's in Ruby 2.0. And so now if you go to measure again, we're better than twice as fast. And it's still quadratic time. It's still slower than you might like, but it's a lot better than it was. And so that's where it stands. So there's a link to the recipe I mentioned for how to get a call graph profiler of Ruby. A link to those patches, which includes instructions for how to use them for your own Ruby build, and then the patch approach.
Cool. Is it in the RC? The release
Uh,
candidate?
I haven't been following the release candidates. You want to repeat it? I'll repeat it.
Is it in the RC1?
I haven't looked at the RC1. It got committed into Subversion back in November, so it should be. Unless they reverted and tell me.
Is this what, I've heard something about a Falcon patch, is this a Falcon patch? Or?
So the Falcon is the handle of a guy named Yuri Sokola. Damn, I'm forgetting his name. But his handle is Falcon, Funny Falcon. So he has a series of patches for Ruby performance. 2 of them are designed to solve the same problems that these patches solve. So the ultimate difference is that these patches are in Ruby 2.0, and those patches existed but never did get into mainline. And there are differences in technique which are part of why that happened, in particularly making the patch cleaner to integrate.
So I've been playing around with Ruby Prof lately.
Okay.
I don't know if it works for 2.0. It's pretty constantly updated, but I don't know how recent it is. But it does the same kind of thing where it can show you like the call graph stuff. Have you looked at
And
that at all? Or?
That's for profiling Ruby code itself, so it shows you the Ruby call graph.
Yeah.
Yeah. So I actually don't know much about profiling Ruby code itself.
Okay.
I've heard from other people that Google perf tools, which have Ruby bindings, perf tools at RB, maintained by a guy on GitHub, that those are good for that purpose. But I don't know much other difference.
Okay. Yeah, I guess you're profiling on a lower level. So.
Yeah. Anybody else?
Did you test this on Windows? The reason why I'm asking is because I upgraded on, we have an XP machine that we have to run code on. And
I have not tested this on Windows. I don't know a reason why it would behave differently on Windows
Okay.
than other systems.
Because it takes like a minute and a half to start.
All right, well, let me know how well it speeds it
I
up.
won't even.
Sounds terrible.
It is. I don't have a choice.
Anybody else? Awesome, that was cool.